Every second of your life, somewhere beyond the edge of what we can see, reality might be branching. Not metaphorically, not in some poetic sense. Actually splitting into countless versions, each one as real as the room you are sitting in right now. This is not science fiction. This is a serious scientific proposition that some of the most respected physicists in the world take seriously. The idea that our universe, everything we have ever known or observed or measured, might be just one bubble in an infinite foam of universes. Each bubble with its own laws, its own constants, its own version of physics. Some of them hostile to life, some of them unimaginably strange. And perhaps, just perhaps, some of them almost identical to ours, containing versions of you making slightly different choices. The concept sounds absurd. It should sound absurd. For most of human history, we believed the Earth was the center of everything. Then we learned it was just one planet among several. Then that our sun was one star among billions. Then that our galaxy was one among trillions. Each discovery pushed us further from the center, made us smaller, made our cosmic address longer and less special. Multiverse is the next step in that humbling progression. It suggests that even our entire observable universe, that sphere of space 93 billion light-years across containing 2 trillion galaxies, is just one instance among infinitely many. The scale is difficult to grasp because it violates every instinct we have about reality. Here is where it gets strange. Multiple independent lines of reasoning in physics all point toward the same conclusion. They arrive from different directions using different mathematics, addressing different problems. Yet they converge on this idea that what we call the universe might be just one region of something vastly larger. Cosmologists studying inflation arrive at it. Quantum physicists working on measurement problems arrive at it. String theorists calculating possible configurations arrive at it. When different branches of physics independently suggest the same radical conclusion, scientists start paying attention. The multiverse is not the goal of these theories. It is an unexpected, often unwelcome consequence that keeps appearing in the mathematics. The story begins, like many cosmological stories, with a problem. In the early 1980s, physicists trying to understand the Big Bang encountered several deep mysteries. Why was the universe so uniform? Looking in opposite directions in space, we see regions that are separated by such vast distances that light has never had time to travel between them. They have never been in contact, never exchanged energy or information. Yet their properties, their temperature, their density are identical to within 1 part in 100,000. How did these causally disconnected regions know to be the same? This is the horizon problem. Then there is the flatness problem. The geometry of space appears to be perfectly flat, balanced on a knife edge between positive and negative curvature. The initial conditions at the Big Bang would have needed to be fine-tuned to 1 part in 10 to the 60th power to produce the flatness we observe. That level of precision seems impossible to achieve by chance. In 1981, a young physicist named Alan Guth proposed a solution. He suggested that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. During this inflationary epoch, space expanded faster than the speed of light, doubling in size every tiny fraction of a second, in less than 1/1,000,000th of a trillionth of a trillionth of a second. A region smaller than an atom inflated to larger than a galaxy. This solves the horizon problem because all the regions we now observe, though now separated by vast distances, came from a tiny patch that was once in contact, in thermal equilibrium. It solves the flatness problem because inflation stretches space so dramatically that any initial curvature gets smoothed out, like inflating a balloon makes its surface appear flatter. The idea was elegant. It was testable. And over the following decades, observations confirmed predictions of inflation. The cosmic microwave background, that ancient light from when the universe was only 380,000 years old, shows exactly the pattern of tiny temperature fluctuations that inflation predicts. Satellites like COBE in 1992, WMAP in 2001, and Planck in 2009 measured these fluctuations with increasing precision. The agreement between theory and observation is remarkable. Inflation has become the standard model of the early universe. But inflation comes with consequences that its creators did not initially anticipate. Here is the problem. Once inflation starts, it is very difficult to stop everywhere at once. The process that causes exponential expansion is driven by a field called the inflaton field, sitting in a high energy state. Think of a ball balanced on top of a hill. For inflation to end, the field needs to roll down to a lower energy state, like the ball rolling down into a valley. But quantum mechanics introduces randomness at small scales. While the field is rolling down in most places, quantum fluctuations can occasionally push it back up in some regions. Those regions keep inflating while others stop. The inflating regions expand so fast that they create new space faster than the non-inflating regions can fill it. So you get more inflation, which creates more space, which gives more opportunities for quantum fluctuations, which create more inflating regions. The process becomes eternal. This is eternal inflation, developed primarily by Andrei Linde, Alexander Vilenkin, and others in the 1980s. It is not a separate theory. It is what happens when you apply quantum mechanics to the inflation that already explains our observations. The mathematics is clear. Once inflation starts in the early universe, it generically never completely stops. Instead, it creates an infinite, ever-expanding fractal structure. Bubbles of space, regions where inflation has ended and ordinary physics takes over, form within a larger inflating background. Our observable universe is one such bubble. Everything we see, all 2 trillion galaxies, formed within one bubble where inflation ended roughly 13.8 billion years ago. But beyond our cosmic horizon, inflation continues, spawning more bubbles, each one a universe unto itself. Think about that for a moment. Each bubble is causally disconnected from all the others. No information can pass between them because they are separated by regions of space that are themselves inflating faster than light. Each bubble could have different physical properties depending on exactly how the field settled when inflation ended there. Different values for fundamental constants, different particles, different forces. The physics we experience might not be the only physics possible. Our universe's properties, the ones that allow stars and planets and life, might be just one outcome among countless others. Now, something else is happening in a completely different area of physics. In 1957, a graduate student named Hugh Everett proposed a radical solution to the measurement problem in quantum mechanics. Quantum theory describes particles existing in superpositions, being in multiple states simultaneously until measured. An electron can be spinning both up and down at the same time. Schrödinger's cat is both alive and dead. But when we measure, we see only one outcome. The standard interpretation says the act of measurement causes the wave function to collapse, randomly selecting one outcome. But this raises uncomfortable questions. What counts as a measurement? What makes it special? Why does observation change physical reality? Everett said the wave function never collapses. All possible outcomes of a quantum measurement actually occur. When you measure an electron's spin, the universe splits. In one branch, you observe spin up. In another branch, you observe spin down. Both versions of you are equally real, existing in parallel. They cannot communicate because they have decohered, becoming entangled with different versions of the environment. This is the many worlds interpretation. It sounds like wild speculation, but it is actually the most conservative approach in one sense. It takes quantum mechanics completely seriously, with no additional collapse mechanism. The equations alone, followed to their logical conclusion, imply branching realities. The number of worlds in many worlds interpretation is staggering. Every quantum event with multiple possible outcomes creates new branches. A photon hitting a half-silvered mirror either reflects or transmits, creating two branches. A particle decaying has various decay modes, creating branches for each. Quantum events happen constantly, everywhere, at microscopic scales. The branching is continuous and rapid. In the time it takes you to read this sentence, the number of branches containing versions of you has increased by an amount impossible to calculate. Each branch is a complete universe with its own future evolution. Most branches are nearly identical to ours in the near term. But over time, small quantum differences accumulate, leading to diverging histories. Here's where it gets uncomfortable. Many worlds is not just about particles in labs. It applies to everything, including macroscopic events that have quantum origins. Genetic mutations are quantum events. Neural firings have quantum components. Weather patterns depend on initial conditions sensitive to quantum fluctuations. Historical events, the outcomes of wars, the existence of particular people, all trace back eventually to quantum randomness. In some branches, dinosaurs never went extinct. In others, humans never evolved. In others still, civilizations rose and fell that never existed in our history. Every possible quantum history, consistent with the laws of physics, is realized in some branch. The implications are staggering. Many worlds suggests that every version of history that could have happened did happen somewhere in the vast branching structure. This is not the same as the bubble universes from eternal inflation. Those are separate regions of space with potentially different physical laws. Many worlds are parallel realities existing in an abstract configuration space called Hilbert space, all governed by the same quantum laws but manifesting different classical outcomes. The two ideas, eternal inflation and many worlds, are independent multiverse concepts arising from completely different areas of physics. Yet both suggest we are not alone as a universe. But there's a problem. A third line of reasoning comes from string theory, the attempt to unify quantum mechanics and gravity. String theory proposes that fundamental particles are actually tiny vibrating strings. Different vibration modes correspond to different particles, like different notes on a violin string. The mathematics is beautiful but requires extra dimensions beyond the three of space and one of time we experience. These extra dimensions must be tiny, curled up at scales too small to observe. The way they curl up determines what physics looks like in the large dimensions we inhabit. Leonard Susskind and others discovered that there are an enormous number of ways to curl up the extra dimensions. Each configuration produces different low-energy physics, different particles, different force strengths, different values for physical constants. The number of possible configurations is often quoted as 10 to the 500 or more. This collection of possibilities is called the string theory landscape. If string theory is correct, and if eternal inflation is correct, then as different bubble universes form, they might settle into different points on the landscape. Each bubble would have different physics, drawn from the vast menu of possibilities string theory provides. Our universe's specific properties, the particular values of constants that allow life, would be just one point on this landscape, realized in our bubble. This connects to a puzzle that has troubled physicists for decades. The laws of physics contain roughly 30 numbers, fundamental constants that are not predicted by theory but must be measured experimentally. The mass of the electron, the strength of the electromagnetic force, the cosmological constant. These numbers appear arbitrary. They could, as far as we know, have been different. But if they were even slightly different, the universe would look nothing like ours. Change the electromagnetic force strength by a few percent and atoms cannot form. Change the mass ratio of protons to neutrons slightly and you get no stable nuclei. Change the cosmological constant by a factor of 2 and space expands so fast that galaxies never form. Our universe sits in a narrow range of parameter space where complexity is possible. Stars can form. Stars can create heavy elements. Planets can exist. Chemistry can happen. Life can emerge. This seems like an extraordinary coincidence. Why should the universe be fine-tuned for our existence? One possible answer is that it is not fine-tuned at all. If there are many universes with different constants, then we necessarily find ourselves in one of the rare universes where life is possible. This is the anthropic principle applied to cosmology. We observe a life-friendly universe not because the universe was designed for life, but because only life-friendly universes contain observers to do the observing. The anthropic reasoning makes many physicists uncomfortable. It feels like giving up on finding deeper explanations for physical constants. If we can just say they are random draws from a multiverse distribution, what motivation is there to seek underlying principles? But the alternative might be worse. Without a multiverse, we are left explaining why the one universe that exists happens to have properties precisely calibrated to allow our existence. That explanation either requires accepting an absurd coincidence or invoking design, which is not a scientific explanation. The multiverse, whatever its philosophical issues, provides a framework where our universe's special properties are selection effects rather than miracles. Calculate what happens if the cosmological constant was different. This number, measuring the energy density of empty space, is famously puzzling. Quantum field theory predicts it should be enormous, about 10 to the 120 times larger than what we observe. That prediction is wrong by more than any other in physics. Yet the observed value is not zero either. It is small but positive, causing the expansion of the universe to accelerate. If it were zero, we would not have acceleration. If it were much larger, even by a factor of 10, the universe would have expanded so fast in its early stages that matter could never have clumped together to form galaxies and stars. The observed value sits in a tiny window. In a multiverse where different bubbles have different cosmological constants, most bubbles would be sterile. Only the rare ones with small values could host life. We find ourselves in such a rare bubble because that is the only place observers can exist. Something else was happening while physicists developed these ideas. Astronomers were discovering just how much universe exists beyond what we can see. The observable universe has a boundary, the cosmic horizon, determined by the speed of light and the age of the universe. Light from beyond, roughly 46 billion light-years, that is the current distance accounting for expansion, has not had time to reach us. We cannot see it, cannot receive information from it, cannot observe it in any way. But there is no reason to think space stops at that boundary. The cosmic microwave background observations show that space is flat or very close to flat. If space is exactly flat, which the data suggests to high precision, then it is likely infinite in extent. That means there is infinitely more universe beyond what we observe. In an infinite space with finite density, every possible configuration of matter must repeat. There are only so many ways to arrange particles within a given volume. The number is huge, but finite. 10 to the 118 for a region the size of our observable universe, roughly speaking. If space is infinite, then every possible arrangement occurs infinitely many times. That includes exact copies of our observable universe. Somewhere out there, impossibly far beyond our cosmic horizon, exists another region identical to ours. Same galaxies, same stars, same Earth, same you, reading these same words. Not just one copy, infinitely many. Some are identical. Others differ by one particle. Others differ more significantly. Every possible variation exists somewhere in an infinite universe. This is not the multiverse of eternal inflation or many worlds. This is just what infinite space implies, even in a single universe with fixed physical laws. It is perhaps the most conservative form of multiverse, requiring only that space extends forever and has roughly uniform properties. If that is true, then we are not alone even without invoking inflation or quantum branching. There are other versions of you out there living other lives, making other choices. They are causally disconnected, unreachable beyond the horizon, but they exist in space, made of matter and energy, following the same laws of physics. The scale required for repetitions is enormous. The nearest identical region would be roughly 10 to the 10 to the 29 meters away. That number is so large, it is meaningless. For comparison, the observable universe is about 10 to the 26 meters across. The distances involved make interaction impossible, but existence does not require interaction. The various multiverse ideas exist on different levels, as the cosmologist Max Tegmark has described. Level 1 is the infinite space multiverse, where distant regions have different configurations but same laws. Level 2 is the eternal inflation multiverse, where different bubbles can have different physical constants. Level 3 is the quantum many worlds multiverse, where all quantum outcomes are realized in branches. Level 4 is the most speculative, the mathematical universe hypothesis, which proposes that all mathematically consistent structures exist physically. Each level is more radical than the last. But even the most conservative level, infinite space, implies we are not the only universe if we define universe as an observable region with particular properties. Think about the implications for existence. If many worlds is correct, there are versions of you who made different choices at every juncture. Versions who took the job, who stayed home, who said yes, who said no. Not just conscious choices, versions where a cosmic ray struck a different neuron, leading to a different thought, cascading into a different life. Every possible timeline consistent with quantum mechanics exists. In some, you live longer. In some, shorter. In some, you never existed at all because a quantum event prevented your conception. The totality of your existence across all branches is vastly larger than your experience in this single thread. If eternal inflation is correct, there are universes with different physics. Some have different particle types. Some have 5 forces instead of 4. Some have different numbers of dimensions. Most are probably simple and sterile, unable to support complexity. But among the infinite variety, there should be bubbles with conditions similar to ours, capable of producing life, though perhaps life very different from what we know. Silicon-based instead of carbon, existing in different states of matter, arising through different chemical pathways. The space of possibilities for life expands dramatically when we consider different physical laws. What we think of as universal requirements for life might just be local requirements in our particular bubble. This creates a troubling question about observation and reality. Science proceeds by making predictions, testing them with experiments, and refining theories based on results. This process assumes that what we observe is representative of objective reality. But if we are in a multiverse, our observations might be biased by selection effects. We observe a universe that allows observers, which is not a random sample from all possible universes. It is like asking fish what the universe is like and getting the answer that everywhere is wet and full of water. The fish see a biased sample because they can only exist in water. We might be cosmic fish, observing conditions necessary for our existence, but mistaking them for universal truths. The multiverse idea raises deep questions about scientific testability. A theory is scientific if it makes predictions that could potentially be proven wrong. But if a theory predicts that all possible outcomes occur somewhere in a multiverse, what does it actually predict about our particular observations? If every version of history happens in some branch of the quantum wave function, the many worlds interpretation does not tell us which branch we will experience. It seems unfalsifiable, more philosophy than physics. Yet many worlds follows directly from taking quantum mechanics seriously. It is not an extra hypothesis added to physics, but a consequence of applying the theory universally without additional collapse postulates. Eternal inflation faces similar challenges. We cannot observe other bubble universes because they are beyond our cosmic horizon, causally disconnected. No signal from them can reach us. No experiment can directly detect them. Yet eternal inflation is a consequence of combining inflation, which we have good evidence for, with quantum field theory, which is the most precisely tested theory in physics. The multiverse is not a theory proposed to explain observations. It is a consequence of theories proposed to explain different observations, taken to their logical conclusions. This is an important distinction. Scientists did not invent the multiverse to solve problems. The multiverse emerged from equations developed for other purposes. But there is a problem with completely untestable ideas in physics. If we allow theories that predict unobservable entities, where do we draw the line? How do we prevent physics from becoming untethered from experiment and drifting into pure mathematics or metaphysics? This tension has created genuine debates within the physics community. Argue that the multiverse, while possibly true, is not science because it cannot be tested. Others argue that it is a natural consequence of our best theories, and therefore should be taken seriously. The debate is not about personal preference, but about the nature of science itself. Yet perhaps the multiverse is not entirely untestable. Eternal inflation makes predictions about the distribution of properties across bubble universes. If we can calculate this distribution and show that universes with our properties are typical, that provides some support. If our properties appear fine-tuned, even accounting for anthropic selection, that counts against the multiverse explanation. The cosmological constant is an interesting case. Its value is small, but not the smallest it could be while still allowing galaxies to form. Some calculations suggest the observed value is roughly what we would expect if we were typical observers in a multiverse where the cosmological constant varies. This is weak evidence, but it is something. The cosmic microwave background might contain subtle signatures of collisions between bubble universes. If our bubble formed near another bubble during eternal inflation, the collision might have left a pattern in the ancient light we observe. Several teams have searched for such patterns. So far, nothing definitive has been found, but the searches continue with improving sensitivity. A positive detection would be revolutionary. Even a non-detection provides constraints on multiverse models, ruling out scenarios that predict frequent observable collisions. The absence of evidence is not evidence of absence, but it narrows the possibilities. quantum mechanics might offer another route. If we could ever decisively test between the many worlds interpretation and collapse interpretations, we would learn something fundamental about the nature of reality. Experiments looking for deviations from pure quantum evolution, tests of macroscopic superposition, searches for objective collapse mechanisms, all contribute to this question. None have found evidence for collapse. The data consistently supports unitary evolution, which is what many worlds assumes. Again, this is not proof, but it shifts probabilities. String theory might be testable in ways we have not yet conceived. The landscape of possible configurations is vast, but perhaps there are principles that constrain where eternal inflation tends to settle. If we could predict the distribution of physical constants and show that observed values are probable in that distribution, that would support the string landscape multiverse. If observed values appear improbable, even accounting for selection, that would count against it. The challenge is that string theory has not yet made clear predictions about low-energy physics. The landscape might be so large that almost anything is possible somewhere, making predictions difficult. Consider what this means for our cosmic address. If we live in an infinite space with repetitions, our address includes position within that infinite space, but also specification of which identical region we mean. A question without operational meaning. If we live in one bubble among eternally inflating multitudes, our address includes which bubble, described by its physical constants and formation history. If we live in one branch of the quantum wave function, our address includes the entire history of quantum outcomes that led to this particular branch. And if we live in one mathematical structure among all possible structures, our address is the specification of our particular mathematical laws. The cosmic address becomes not just lengthy, but infinitely complex. Humans have always wondered whether we are alone. For most of history, the question meant alone in the universe. Are there other planets, other stars, other galaxies? The answer has been a continuous expansion of cosmic real estate. Then the question became whether there is other life, other intelligence. We still do not know that answer, but the discovery of thousands of exoplanets suggests conditions for life might be common. Now the question has shifted to whether our entire universe is alone. Are there other realms of existence? Other domains of space and time? Other realities? The multiverse concept expands the scope of that question to almost unimaginable scales. This is not just abstract philosophy. It affects how we interpret observations. When we measure a physical constant and find it has a particular value, we used to assume that value had a deep explanation, that it was determined by some principle we had not yet discovered. If the multiverse is real, some constants might have no deeper explanation. They are environmental facts about our region, like the distance from Earth to the Sun. That distance is important for life on Earth, but it is not a fundamental law. It is an accident of how the solar system formed. In a multiverse, some of what we thought were fundamental laws might be accidents. The weak nuclear force provides an example. It governs radioactive decay and plays a crucial role in how stars burn. The strength of this force determines the fusion rates in stellar cores. Change it significantly, and stars would behave very differently, either burning too fast and dying quickly, or burning too slow and never producing heavy elements. The observed strength allows long-lived stars that create the elements necessary for planets and life. For decades, physicists sought a deep principle explaining why the weak force has its particular strength. But if there is a landscape of possibilities, and eternal inflation populates them, the weak force strength might just be what it needs to be for stars to work properly. We observe this value because only bubbles with similar values produce observers. Watch what happens when we extend this logic. If enough physical parameters are environmental rather than fundamental, we lose predictive power. We cannot calculate values from first principles if they are random draws from distributions. We can only observe them and apply anthropic reasoning to explain why they fall in life-allowing ranges. This bothers many physicists who entered the field hoping to find elegant mathematical reasons for the structure of nature. The multiverse can feel like a retreat from that goal, an admission that some questions have no answers beyond, "That is how it happened to be here." But maybe that discomfort comes from aesthetic preferences rather than logic. Nature is not obligated to satisfy our desire for elegance. The universe does not have to be fully explainable from first principles. If we lived in a multiverse, we would expect to find ourselves in a region whose properties allowed our existence, even if those properties seem arbitrary from a fundamental perspective. The fact that physical constants appear fine-tuned for life is exactly what the multiverse predicts, combined with anthropic selection. The alternative is to believe we won a cosmic lottery with odds of 1 in billions of billions by pure chance, or to invoke explanations outside of science. There exists a more troubling implication that physicists rarely discuss in public. If the multiverse is real and infinite, then not only does every possible quantum outcome occur, but every possible configuration of matter occurs, including ones that arise by pure chance. In an infinite universe, thermodynamic fluctuations will occasionally produce organized structures. A random fluctuation could produce a star. Given enough time and space, a fluctuation could produce a galaxy. It could even produce a brain, fully formed with memories and thoughts, appearing spontaneously out of the void. These are called Boltzmann brains, after the physicist Ludwig Boltzmann. Here is where it gets uncomfortable. In an infinite universe, Boltzmann brains should vastly outnumber normal, evolved brains like ours. It takes enormous cosmic effort to produce a brain the normal way. You need stars to make heavy elements. You need planets to form. You need billions of years of evolution. But random fluctuations will try every configuration eventually. It is far more probable for a fluctuation to produce just a brain with false memories of a past that never happened than to produce an entire universe with a consistent history leading to that brain. If you are a random observer in an infinite universe, you are more likely to be a Boltzmann brain than a real, evolved human. This is deeply disturbing because, if you are a Boltzmann brain, your memories are false, your observations unreliable, your reasoning about the universe suspect. You could not trust that you are actually reading these words. You could not trust your memories of learning physics. You could not trust anything. The Boltzmann brain problem threatens to undermine the entire scientific enterprise. If our best theories predict that we are most likely random fluctuations with false memories, those theories predict that we cannot trust the reasoning that led to them. The theories become self-defeating. Cosmologists take the Boltzmann brain problem seriously. It is used as a test of cosmological models. Any model that predicts we are likely to be Boltzmann brains is rejected, not because we do not like the conclusion, but because such a model makes itself untestable. We assume we are real observers with genuine histories because if we are not, science is impossible. Models of the multiverse must be constructed carefully to avoid producing too many Boltzmann brains. This typically requires that the universe has a finite lifetime or that the dominant energy in the late universe has specific properties. The observed positive cosmological constant helps. It causes accelerated expansion that eventually dilutes matter, ending the era when fluctuations can produce complex structures. This cuts off Boltzmann brain production before it overwhelms normal observers. Think about what we are doing here. We are using observations of the universe's expansion to constrain multiverse theories to avoid a paradox about the nature of consciousness and observation. This is science at its most abstract, dealing with questions that feel almost philosophical. Yet the logic is rigorous. If a theory predicts observers like us should not exist or should be outnumbered by random fluctuations, that theory is in trouble. The multiverse must be structured in a way that makes real observers typical rather than rare. This requirement constrains the possibilities. Recent advances in cosmology have refined our understanding of inflation and its consequences. The Planck satellite, which stopped collecting data in 2013, but whose full analysis continued for years after, measured the cosmic microwave background with unprecedented precision. The results strongly support inflation. The predicted pattern of temperature fluctuations matches observations exquisitely. But there is more. The measurements constrain the type of inflation that occurred. The data favors simple, single-field inflation models over more complex alternatives. This narrows the possibilities for what happened in the first moments of the universe. But the data does something else. The fluctuations in the cosmic microwave background are almost exactly scale invariant, meaning they have similar amplitudes at all observable sizes. This is a prediction of inflation, but they are not perfectly scale invariant. There is a slight tilt, a small deviation that inflation also predicts. The measured tilt is about 96/100ths, meaning slightly more power on large scales. Different inflation models predict different tilts. The observed value rules out some models and favors others. As measurements improve, the constraints tighten. We are closing in on the specific mechanism that drove inflation in the early universe. Understanding the specific inflation mechanism matters for eternal inflation. Not all inflation models lead to eternal behavior. If the inflaton field has certain properties, inflation can end everywhere without generating an eternal fractal structure. Other models almost inevitably produce eternal inflation. The observations from Planck and other experiments help determine which category our universe falls into. Current data leans toward models that do produce eternal inflation, though the conclusions are not definitive. The question remains open, but we are making progress. The cosmic microwave background holds other clues. Inflation predicts not just density fluctuations, but also gravitational waves, ripples in space-time produced by the violent expansion. These gravitational waves leave a distinctive signature in the polarization of the cosmic microwave background, called B-mode polarization. Detecting this signature would confirm inflation directly and measure its energy scale. Several experiments are searching for B-modes. In 2014, the BICEP-2 experiment announced a detection, causing enormous excitement. But further analysis showed the signal was contaminated by dust in our galaxy. The primordial B-mode signal, if it exists, is still hiding below the noise. Next-generation experiments are being designed with the sensitivity to detect primordial gravitational waves if they exist at levels many models predict. The Simons Observatory, CMB-S4, and proposed satellite missions aim to improve sensitivity by orders of magnitude. A detection would revolutionize cosmology. It would confirm inflation, measure the energy scale of the early universe, and provide crucial data about what drove expansion. A non-detection after exhausting sensitivity would rule out certain classes of inflation models and constrain how the multiverse, if it exists, came to be. Quantum mechanics experiments are also advancing in ways relevant to multiverse questions. Researchers have created quantum superpositions of ever larger systems. Individual atoms were routine decades ago. Molecules containing dozens of atoms are now standard. Recent experiments have achieved superpositions of objects containing thousands of atoms, massive enough to be visible under a microscope. Each increase in scale tests the boundaries between quantum and classical behavior. So far, quantum mechanics holds. There is no sign of where superpositions break down and collapse into definite states. If quantum mechanics is truly universal, with no collapse mechanism, then many worlds or something like it follows. The experimental program is to keep pushing to larger systems, looking for deviations. If a collapse mechanism exists, it should manifest when objects reach some critical size or complexity. Theories of objective collapse, like the GRW model or Penrose's gravity-induced collapse, make predictions about where quantum behavior gives way to classical. Tests of these predictions have consistently ruled out collapse in the regimes tested so far. The upper limit on system size for quantum behavior keeps rising. This does not prove many worlds, but it makes alternatives harder to maintain. There is something profound about the testability debate. Even if we can never directly observe other universes, the multiverse idea comes from theories that are testable in our universe. Inflation makes predictions about the cosmic microwave background. Quantum mechanics makes predictions about particle behavior. String theory, when sufficiently developed, might make predictions about particle physics. We test these theories here, in our accessible reality. If the theories are correct, and if their logical consequences include a multiverse, then we have indirect evidence for the multiverse. This is not the same as direct observation, but it is how much of science works. Consider particle physics. Quarks have never been observed in isolation. They are always confined within protons and neutrons. We cannot pull a quark out and look at it. Yet we are certain quarks exist because the theory that includes them, quantum chromodynamics, makes countless predictions that match observations. The existence of quarks is inferred from indirect evidence, not direct observation. The multiverse might be similar. We might never see another universe, but if the theories that imply them keep succeeding in testable predictions, belief in the multiverse becomes rational. The strongest argument against the multiverse is not that it is untestable, but that we might be able to explain observations without it. If someone discovers a principle that determines the values of physical constants from pure mathematics, eliminating their apparent arbitrariness, the anthropic argument loses force. If someone finds a mechanism that solves quantum measurement without many worlds, that alternative might be preferable. If inflation can be modified to avoid eternal behavior while keeping its successful predictions, eternal inflation becomes unnecessary. The multiverse is the best explanation we currently have for certain puzzles, but it might not be the final explanation. But it might not. The multiverse might be reality. We might inhabit one of countless bubbles in an eternally inflating space. We might be one branch among innumerable quantum branches. We might exist in a region of infinite space that repeats our exact configuration infinitely many times at incomprehensible distances. All three could be true simultaneously. The levels of multiverse might stack, with quantum branches within inflation bubbles within infinite space. The full reality could be vastly richer than our small corner suggests. Let your mind expand to encompass that possibility. Everything you see, everyone you know, all of human history, every star in the night sky, every galaxy in our deepest images, all of it is one tiny bubble or one quantum branch in something beyond measure. The scale makes human concerns seem microscopic, yet those human concerns are all we directly experience. The multiverse, if real, does not diminish the importance of this reality. This is the only branch you experience, the only bubble you inhabit. Its reality to you is absolute. Philosophers have long debated questions about identity and existence that the multiverse brings into sharp focus. If there are infinitely many copies of you in distant regions of space, which one is the real you? The question assumes uniqueness that might not exist. Perhaps you are all of them, a distributed entity across space. Or perhaps personal identity is local, defined by continuity of experience rather than physical duplication. A copy of you, even if atom for atom identical, is not you in any meaningful sense if there is no causal connection, no shared experience. The multiverse forces us to refine what we mean by individual existence. Many worlds raises similar questions. If the universe branches with every quantum event, creating versions of you making different choices, is there a single you, or are you a multiplicity? Before a measurement, all branches exist in superposition, described by a single wave function. After the measurement, the branches decohere but remain parts of the same universal wave function. In a sense, all versions of you continue to exist within that wave function. They just cannot communicate. Personal identity becomes a local phenomenon tied to one branch's experience. The you that exists from your subjective perspective is the you in this branch, even though other versions exist elsewhere in Hilbert space. These are not just abstract philosophical puzzles. They connect to real questions about probability and prediction. In a multiverse where all outcomes occur, what does it mean to say one outcome is more likely than another? In many worlds, both outcomes of a quantum measurement occur. The wave function assigns them amplitudes, which standard quantum mechanics interprets as probabilities. But if both happen, why do amplitudes matter? The answer involves the Born rule, which says the probability of experiencing an outcome equals the squared amplitude of that branch. This rule is built into quantum mechanics but feels somewhat mysterious in many worlds. Why should you expect to find yourself in a high amplitude branch more often than a low amplitude branch, if all branches exist? Various attempts have been made to derive the Born rule from more fundamental principles within many worlds. Some appeal to decision theory, arguing that rational agents should make choices as if probabilities equal squared amplitudes even in a multiverse. Others use symmetry arguments or appeals to typicality. None are entirely satisfying, but the question remains a focus of research. If many worlds cannot explain why we observe probabilities matching the Born rule, it faces a serious problem. But so far, no observation has contradicted the Born rule, and no better alternative to many worlds has resolved the measurement problem. In eternal inflation, probability questions become even more complex. Different bubble universes have different physical properties. If we want to calculate the probability of observing our particular constants, we need to know what fraction of bubbles have those values. But in eternal inflation, there are infinitely many bubbles of each type. How do you calculate fractions when numerator and denominator are both infinite? You have to introduce a measure, a way of comparing infinities. Different measures give different answers. This is the measure problem in cosmology, and it has no agreed-upon solution. The measure problem matters because it affects what the multiverse predicts. Using one measure, our observed constants might be typical. Using another measure, they might be extremely rare. Without a natural measure, the multiverse loses predictive power. Researchers have proposed various measures based on different physical considerations. Some count bubbles by volume, some by observer number, some by entropy. Each has advantages and problems. The lack of consensus here is a genuine weakness in multiverse cosmology. It is an active area of research, but also a point critics emphasize. Despite these challenges, the multiverse idea has gained acceptance among many physicists, not because it is proven, but because alternatives seem worse. The fine-tuning of physical constants is real. Our universe's properties lie in narrow ranges that allow complexity. Either this is a stupendous coincidence, an artifact of necessity we do not yet understand, a result of design which is not scientific, or a selection effect in a multiverse. Of these options, the multiverse is the only one that fits within the framework of naturalistic explanation while accounting for the data. This does not make it true, but it makes it a serious scientific hypothesis worth pursuing. The history of cosmology is a history of expanding horizons. Ancient humans thought the Earth was all there was. Then we learned about the solar system, then the Milky Way galaxy, then the billions of galaxies beyond. Each expansion was resisted initially. Each seemed to make humans less significant, but each was driven by observations and logic, not preference. The multiverse is the next proposed expansion. It asks us to consider that even the observable universe, vast as it is, might be a tiny part of reality. If history is a guide, our intuitions about what seems reasonable are poor predictors of what is actually true at cosmic scales. Think about the Copernican revolution. For millennia, humans placed Earth at the center of the universe. The idea was intuitive. The ground feels stationary. The sky appears to rotate around us. But observations, particularly of planetary motions, grew increasingly difficult to explain in the geocentric model. Epicycles were added, complicated mathematical devices to account for apparent retrograde motion and other phenomena. The system became unwieldy. Copernicus proposed that the Sun, not Earth, was central. Suddenly the observations made sense. Planets orbited the Sun at different speeds, and their apparent motions from Earth were geometric consequences. The shift was not accepted immediately. It contradicted common sense and scripture. It displaced humanity from a central position. But the evidence accumulated. Galileo's observations of Jupiter's moons showed that not everything orbited Earth. Venus showed phases like the Moon, explicable if it orbited the Sun, but puzzling otherwise. Eventually, the heliocentric model became undeniable. We were not central. Earth was one planet among several, orbiting an ordinary star. Then came the next displacement. In the early 20th century, astronomers debated whether the Milky Way was the entire universe, or just one galaxy among many. The fuzzy nebulae visible in telescopes might be gas clouds within our galaxy, or they might be distant galaxies. In 1923, Edwin Hubble resolved the question by identifying individual stars in the Andromeda Nebula and measuring their distance. Andromeda was far too distant to be part of the Milky Way. It was a separate galaxy. The universe was vastly larger than anyone had thought. Humans went from living in the center of everything to living on a planet orbiting one star among hundreds of billions, in a galaxy that was itself one among hundreds of billions. Every step in this progression involved accepting that we are less special than we thought. The multiverse is the same pattern repeating. Our universe might not be all there is. It might be one of innumerably many. The pattern of displacement has been consistent. Why should it stop now? This is not a proof, but it is a suggestive historical trend. Each time we have been forced to expand our conception of reality, we have resisted, then adapted, then found the new view richer and more interesting than the old. Some physicists argue that the multiverse represents the end of physics, a capitulation to untestable metaphysics. If we cannot observe other universes, we have left the realm of science. But others see it as a natural evolution. Physics has always dealt with unobservables. Atoms were unobservable for decades but were accepted because theories involving them worked. Quarks are unobservable in isolation. Black hole interiors are unobservable from outside. We cannot observe the universe before the timelight began propagating freely. Science frequently makes claims about things that cannot be directly observed, based on theories that can be tested in observable regimes. The multiverse is an extreme case, but not a different kind of claim. The debate about what counts as science is genuinely important. If we allow explanations that invoke unobservable entities with no constraints, we could explain anything by making up convenient stories. Dragons are pushing planets around but cannot be detected. Invisible elves determine physical constants. Without testability, these become unfalsifiable. Science works because it is constrained by observation. Theories must make predictions that could be wrong. The multiverse seems to violate this principle. But the situation is more subtle. The multiverse itself might not be testable, but the theories that imply it are testable. We test inflation, quantum mechanics, string theory. If they keep working, and if they necessarily lead to a multiverse, we gain confidence in the multiverse indirectly. This is Bayesian reasoning. We update our beliefs based on evidence. Direct evidence for a claim is strongest, but indirect evidence matters too. If theory A predicts observation X and observation Y, and multiverse Z, and we confirm X and Y, our confidence in Z increases even if we cannot test Z directly. This is how science often works. We believe in the interior structure of the sun not because we have drilled into it, but because the theory that describes that interior also explains the light and neutrinos we observe. The multiverse stands or falls based on whether the theories that produce it continue to succeed in testable domains. Current observations provide some intriguing hints, though nothing conclusive. The cosmic microwave background is remarkably uniform, as inflation predicts, but it also has subtle anomalies. There is a slight asymmetry in power between hemispheres. There is a lack of correlation on the largest scales. These anomalies are at low statistical significance, around 2 to 3 sigma, meaning they could be random fluctuations. But if they are real, they might indicate something unusual about the early universe. One possibility is that they reflect our position near a feature in the larger inflating space, perhaps the remnant of a bubble collision, or the finite size of our bubble. Researchers have searched the cosmic microwave background for circular patterns that might indicate collisions with other bubbles. The idea is that if another bubble collided with ours during inflation, it would leave a circular imprint in the sky, a region with slightly different temperature. Several groups have performed these searches. Some have claimed tentative detections, but none have been confirmed. The statistical significance is low, and the patterns could be random noise. The absence of clear signals constrains how often bubbles collide, which constrains models of eternal inflation. If collisions were common, we should see their signatures. Either they are rare or our methods are not sensitive enough, or eternal inflation is not correct. Watch what happens in the next decade. Several major observational programs will provide new data relevant to multiverse questions. The James Webb Space Telescope, launched in 2021, is observing the earliest galaxies. By seeing how structure formed in the early universe, we learn about the initial conditions set by inflation. The Vera Rubin Observatory, expected to begin full operations in the mid-2020s, will map billions of galaxies, tracing large-scale structure with unprecedented detail. The distribution of galaxies constrains cosmological models, including aspects of inflation. Gravitational wave detectors are opening a new window on the universe. LIGO and Virgo detect waves from black hole and neutron star mergers. Future detectors like LISA, a space-based interferometer planned for the 2030s, will observe lower frequency waves, including potentially those from the early universe. Primordial gravitational waves, if they exist, carry information about the inflation era. Detecting them would be a Nobel Prize-level discovery and would help determine what kind of inflation occurred. Particle physics might contribute unexpected insights. The Large Hadron Collider has not found evidence of supersymmetry or other new physics beyond the Standard Model. This is puzzling because many physicists expected new phenomena at accessible energies. The absence might mean that new physics exists at higher energies than we can reach, or it might mean some theoretical ideas are wrong. Understanding why the Higgs boson has its particular mass and why the universe did not collapse in the early high-energy conditions relates to fundamental questions about the stability of physical laws and the landscape of possibilities. Advances in quantum computing and quantum simulation might allow tests of quantum mechanics at new scales and complexities. If we can create and manipulate larger quantum systems, we can test the boundaries of superposition and entanglement. This might never settle the question of interpretation definitively, but it will constrain what kinds of modifications to standard quantum mechanics are possible. Each experiment that confirms quantum predictions in larger systems makes collapse theories harder to maintain, and many worlds correspondingly more plausible. Theoretical work continues on multiple fronts. Researchers are trying to calculate the string theory landscape more precisely, determining what kinds of vacua are actually stable and accessible. Others are working on the measure problem in eternal inflation, seeking a natural way to define probabilities. Some are exploring alternatives to inflation that might solve the same problems without generating a multiverse. Others are developing new tests that might indirectly constrain multiverse properties. The intellectual landscape of physics is in flux. The standard models of particle physics and cosmology are astonishingly successful but incomplete. They leave major questions unanswered. Why these particles? Why these forces? Why these constants? What is dark matter? What is dark energy? How do you unify quantum mechanics and gravity? The multiverse offers answers to some of these questions, but at the cost of invoking vast, unobservable realms. Whether that cost is worth paying depends on whether alternatives emerge that are more satisfying and equally successful. Consider the sheer strangeness of our situation. We are arrangements of atoms that have become aware, able to contemplate our own existence and the nature of reality. We have used that awareness to uncover deep patterns in nature, mathematical laws that govern matter and energy. Those laws, followed faithfully, seem to imply that we are not alone as a universe, that reality is vastly larger than we can observe. The atoms that compose us, forged in stars billions of years ago, are considering the possibility that those stars exist in one bubble of an infinite foam. This is consciousness reflecting on its cosmic context, and finding that context stranger than any myth humans invented. There is something both humbling and elevating about this. Humbling because we are so small, one species on one planet, in one galaxy, in one observable region that might be one of infinite many. The scale reduces human concerns to apparent insignificance. Wars, politics, daily struggles, all happen in a context so local, it almost vanishes against the cosmic backdrop. Yet it is elevating because we can understand this. We are not just subject to these vast scales. We can comprehend them, model them, test ideas about them. The same atoms that make up distant galaxies make up our brains. The laws that govern the multiverse, if it exists, govern our thoughts. We are the universe becoming self-aware, even if we are just one small part of it. The multiverse, if real, does not diminish meaning. It relocates it. Meaning does not come from being unique or central or special by cosmic standards. It comes from the richness of experience, the complexity of consciousness, the web of relationships and understanding we build. Those things are real here, in this branch, in this bubble on this planet. The multiverse would add context, but would not erase what matters locally. Your life is no less real if there are infinite other lives elsewhere. Your choices matter in your causal future, regardless of what happens in other branches or bubbles. The multiverse is about the structure of reality, not the value of existence. This connects to ancient philosophical questions about the nature of being. Why is there something rather than nothing? The multiverse does not answer this. It pushes the question back. Why is there a multiverse rather than nothing? But it changes the shape of the question. If all mathematical structures exist as the most radical multiverse proposal suggests, then perhaps existence is necessary rather than contingent. If all possibilities are realized, there is no alternative to something existing. Nothing would be just one possibility among many, and perhaps not even a coherent one. This is speculative philosophy more than science, but it shows how the multiverse touches the deepest questions humans ask. Different cultures and traditions have imagined multiplicity of worlds before. Ancient Greek atomists proposed infinite worlds arising from infinite atoms. Hindu and Buddhist cosmologies include countless universes existing and dissolving in vast cycles. Indigenous creation stories sometimes feature multiple layers or realms of reality. The idea that our world is not all there is appears across human cultures. What is new is the specific scientific formulation, the connection to tested theories, the mathematical precision. The multiverse is an ancient intuition refined by modern physics into something testable, at least indirectly. As observations improve and theory develops, our understanding will sharpen. We might find evidence that strongly supports the multiverse. We might find evidence that rules it out. Or we might remain in the current state, where it is a plausible consequence of good theories, but not definitively confirmed. Science does not always provide clean answers. Sometimes the honest conclusion is that we do not yet know. The multiverse question might be one where certainty remains elusive for decades or longer, but the pursuit of the answer drives progress. Developing the theories, designing the experiments, refining the observations, all of this advances our understanding even if the ultimate question remains open. We learn about inflation whether or not it is eternal. We learn about quantum mechanics whether or not many worlds is correct. We learn about string theory whether or not the landscape is real. The journey produces knowledge regardless of the final destination. In some distant future, if humanity or its successors survive, we might look back on this era as the moment we first seriously confronted the possibility of the multiverse. Just as we now look back on the Copernican revolution or the discovery of galaxies beyond the Milky Way as pivotal moments in understanding our place. Future beings might mark the early 21st century as when the multiverse shifted from speculation to serious science. Or they might mark it as the beginning of a dead end that was eventually abandoned. Either way, the questions we are asking now are fundamental. Imagine the totality. Infinite space, perhaps, with infinite repetitions of every possible configuration. Eternal inflation generating bubbles continuously, each with different physics. Quantum branching creating new histories with every measurement. Mathematical structures beyond the ones we inhabit, realizing different logical possibilities. The full reality, if these ideas are correct, is beyond human comprehension in detail. We can grasp the outline, the structure, the principles. but the specific content, the actual infinity of worlds and events and beings and histories, exceeds any mind's capacity. Yet here we are in this one corner, this one moment, contemplating it all. The fact that you can understand these ideas, even partially, is itself remarkable. You are a pattern of atoms complex enough to model the cosmos, including the parts you cannot see. That modeling capacity, that ability to conceive of the inconceivable, is what makes humans unique on this planet. It might be rare in the universe, or it might be common. The multiverse implies that somewhere, if space is infinite or bubbles are infinite, intelligence exists in numbers beyond counting. You are one instance of a universal phenomenon, matter organizing itself to understand itself. The search for truth about the multiverse continues. Researchers publish papers, debate interpretations, design experiments, make observations. The scientific community has not reached consensus. Opinions range from confident belief to strong skepticism. This diversity of views is healthy. Science works best when ideas are challenged, when evidence is demanded, when alternative explanations are seriously considered. The multiverse will be accepted or rejected based on how well it explains observations and how well it fits within broader theoretical frameworks, not on how appealing it seems. For now, the question remains open. We are not the only universe in existence space if the theories are right. We might be one bubble in an eternal inflation. We might be one branch in a quantum multiverse. We might be one configuration in infinite space. Or we might be all there is, a single cosmos whose properties remain deeply mysterious, but are determined by principles we have not yet discovered. The data does not yet decide between these options, though it leans in certain directions. As you drift toward sleep, or toward whatever comes next in your evening, let these ideas settle in your mind. The possibility that reality extends far beyond what we can see. That other universes might exist forever beyond our reach, but as real as this one. That every quantum outcome might be realized somewhere in the vast branching structure of possibilities. That your existence, improbable as it seems, is repeated infinitely many times in an infinite space. These thoughts are vertiginous. They can make you feel insignificant, or they can make you feel connected to something incomprehensibly vast. Perhaps the truth is both. You are tiny by cosmic standards, but you are also made of the cosmos. You are not separate from this grand structure. You are part of it. The atoms in your body were forged in stars, scattered by supernovae, gathered into planets, organized into life. Your thoughts are patterns in neural networks that arose through evolution, a process driven by natural selection over billions of years. You are a way the universe has found to know itself. If there are infinite other ways in infinite other places, that does not diminish the reality of this particular way, here and now. The multiverse, if real, is the ultimate expression of cosmic abundance. Not just many planets, not just many galaxies, but many universes. Reality maximized to the point where every possibility is actual somewhere. It is a vision of extravagant creativity, where nature exhausts all options rather than selecting just one. Whether this vision is true or false, it expands our conception of what might be, and that expansion is valuable in itself. It reminds us that the universe is under no obligation to match our intuitions or to comfort our desire for uniqueness. Science has taught us repeatedly that reality is stranger than we imagine. Time is relative. Space curves. Particles exist in superposition. The vacuum is not empty, but seethes with virtual particles. Every result that seemed impossible at first was eventually confirmed by experiment. The multiverse is the latest in this sequence of strange, but potentially true ideas. It has not been confirmed, but it has not been ruled out. It stands as a possibility, grounded in serious theoretical work, waiting for observations to strengthen or weaken the case. If these cosmic mysteries speak to you, if the questions about existence and reality and our place in it all resonate, there are more waiting to be explored. Science is the process of asking nature what is true and listening carefully to the answers. The answers are often surprising, always fascinating, sometimes unsettling, but they are answers about what actually is, not what we wish would be. That commitment to truth, wherever it leads, is what makes science powerful. The multiverse might be the ultimate example. It leads where our best theories point, even though it seems impossible to test fully, and contradicts our intuition that what we see is all there is. Following the logic requires courage and humility. Courage to accept conclusions that make us smaller. Humility to recognize that nature is not constrained by what we find comfortable or comprehensible. Thank you for exploring these ideas, for letting your mind expand to encompass possibilities that stretch the imagination. The universe or multiverse is vast and strange and beautiful in ways we are only beginning to understand. Leave your thoughts in the comments if you found wonder in these cosmic depths. And I will see you in the next one, fellow traveler through space and time, wherever and whenever you are in this vast, strange reality we call home.